Hi, everyone. So first I'd like to point to my co-authors on this paper. And so today I'm going to talk to you about a project in the Canadian Rockies to monitor blister rust infection over time and space. And the monitoring objective that we were focused on was really understanding these two forces, so both time and trying to explain changes or of these other landscape variables. And in 2014, we also coordinated our sampling across a very large landscape, and I'll show you that. So here's our study area, and it extended from Waterton in the south, so here's Waterton, 800 kilometers up to Jasper and up into the Wilmar Wilderness. So a very large study area. And what we were measuring was health status. And so we used the Whitebark Pine Ecosystem Foundation methods to understand blister rust and mountain pine beetle infection rates. And that method focused on measuring permanent plots that were originally installed in 2003 and 04. And we remeasured those in 2009 and again in 2014. And before 2014, there were different jurisdictions installing and measuring these plots. And in 2014, we worked together to try and do one single measurement across the study area. And that complicated the survey effort, but I think is really valuable in trying to reduce variation over time when we remeasure these plots. And so, following the methods, we measured on permanently tagged trees in monumented plots. We measured the presence and absence of blister rust and mountain pine beetle, and the percent canopy kill, and cause of death and regen. And to accomplish all of this, you'll see we had an awful lot of trees. That's over our 3 visits. So almost 40,000 trees in the data set. We had 3 crews working in 2014, and some of the plots were accessible by road, close to road, but the vast majority required a fair bit of hiking and, in some cases, helicopter access. And really, a primary focus at the beginning of the field season was training, because there can be a pretty significant effect of observer on blister rust, on the ability to detect to identify the presence and absence of infection. This study also presented other analytical challenges. So you've got your trees that are nested within plots, and those plots are often clustered at a location. So when they were originally set up, we set up more than one plot in a location because access was such a challenge. And so we had to account for that spatial correlation, but we also had to deal with the temporal correlation. So we used a mixed effects logistic regression model, and with the focus this time on the tree. So in previous analyses, we summarized by the plot, and we looked at infection rates in the plot. But this time, we decided to have the tree be the measure, and I think that's been quite interesting. It's a slightly different approach than we've used in the past. And for this approach, we developed a series of candidate models. And so those candidate models are sort of competing hypotheses about explaining the presence and absence of infection. And the variables that I included were climate variables from the Western North America climate data set, some landscape variables that were measured on-site, and other ones that included latitude, distance to divide, and so on. And then most important is time. And before doing the analysis, I looked at correlation among our variables, and that it limited our ability to include the various some of the variables in the same model. And so this was the best performing model for whitebark pine. We used AIC and then validated the models. And these were the variables that were the important predictors of infection rates. Latitude, distance to divide, which is negative on the BC side and positive on the Alberta side. The DBH of the tree, degree days above 5 degrees Celsius, and time. And so I'll walk you through a few of the relationships between the predictor variable and the response. And so you can see here, this is the probability of infection by blister rust and distance to divide. So on your left-hand side, you're in BC. It increases as you get close to the divide, and then east of the divide, infection rates decline. And I think that probably agrees with a lot of the things that we're seeing out there. And the gray is the 95% confidence intervals. Now this is a relationship with latitude, and I've got a little work to do still in the latitude one, because in our previous paper we saw a decline, high levels in Waterton, lower in the middle range, and high again in the north. And I still think that's what's happening. So, but this is the general trend that came out in our best model, and you can see that that in general, infection rates decline as you move further north in the study area. And these three graphs, there's no interaction effect. It's the same relationship. But it just, this shifting up is just an increase in infection over time. But I'll show that more clearly here. So this is, think Waterton for these southern stands. And you can see that infection rates are very high. And this is for an average sized tree. And you can see infection range of 80 to 90% currently. And then this would be sort of a Jasper latitude. And what I did here was the graph on your left is for a small tree. The graph on the right is a larger tree. And so if you're a small tree in Jasper, infection rates are 20 to 40%. And a larger tree, they're 40 to over 60%. And you can see a slightly increasing rate over time. Anyway, I did use the same approach for the limber pine data. And limber pine only extends as far north as North Banff. There's no limber in Jasper. And the best performing model included these 4 variables. And I'll walk you through these. So this one shows on the left the relationship with size of the tree, and as DBH increases up to the largest trees in the plot, you're infected by blister rust. And then with latitude, I included it in the same way as my models for whitebark pine, and decreasing infection with latitude. Now this is interesting. This is this is infection in the southern stand. So Waterton on the left, really high rates of infection, and tighter confidence intervals in the most recent resurvey. But if you're looking at limber pine in the north, so this would be Saskatchewan River crossing area of Banff, would be an example. Very low infection rates for limber pine. So that's good news. So what I'd like to present now are some applications of the monitoring. So I spend a lot of time monitoring different things than whitebark pine, and one of the frustrations sometimes with monitoring is seeing the results applied. And so I've got a few examples of ways that we can apply what we're learning about whitebark pine to restoration. So the first is to produce maps based on our models. So this is a map of infection rates for blister rust for Waterton to the Wilmore. And it's based on these variables that are spatial from the model. And this will need a little bit of tweaking, but I think it shows pretty clearly that in fact in the Waterton and eastern BC area, and decline as you move further north. And I cut out all the low elevation areas. And the second application was more, we took the data from the plots and calculated a stand density based on those data. And then what I did was I removed all trees that had a high, either top kill or very, very high canopy kill, and removed those out and calculated stand density in meters squared per hectare. And then we combined, so that's on the left, and on the right is the median infection level for that plot. And I wanted to summarize it in a way that would provide different jurisdictions with a sense of where they were at in the study area for these two measures, important measures. And you can see green is good, yellow is there's some concern, and then red is where there's concern for that measure. So Waterton's clearly would be considered, say, a higher priority for restoration, whereas Banff has fairly good conditions for both of those measures. And the Alberta plots and BC plots near the bottom, and the White Goats de Fleur and Wilmore are both provincial parks in Alberta, in the further north area. And then, so taking this kind of information from these measures and applying them for restoration activities, like using maps to help us understand where to target searching for clustering. So a map of blister rust infection rates can help us understand where we've got good access to areas with high infection. So the next steps for me are that together we have to work on completing the analyses. So for mortality as well as regeneration rates, fine-tune some of the mapping, because I think the maps are helpful, but we want to make sure that we get them right. And then lastly is to put together a power analysis, because it would be helpful to reduce the number of plots that we're resampling and still be able to gain the knowledge that we need. So it's an awful lot of plots to commit every 5 years to when there's so much to do for the species. So if we can reduce the number of plots that we visit, that would be a good thing. And these photos are primarily in Jasper, and they're to tempt you all to come next year. So these are our funders and field students